Okay guys, Assalamualaikum warahmatullahi wabarakatuh. My name is Aditya Yudha JR, and I want to explain to you guys how to solve number 7 from my final exam digital electronics subject. Without further ado, let's get into it. So here is the problem. We have to implement the cout, one of the full adder output, using 3-2-1 multiplexer only. Before we getting into the details of it, we have to know the full adder truth table. We can see from the fifth questions how the truth table of the full adder looks like. Now this is the truth table here. It has 3 inputs and 2 outputs. 3 inputs, there are A, B, and sin, and 2 outputs, there are sum and cout. Now, let's get back into the questions number 7. We have to implement the cout, one of the full adder output, using 3-2-1 multiplexer only. First, we have to make the truth table, but in this truth table, we just put only one output, that is cout. We don't use the sum because in the problem, the context using only the cout. Okay, done with the truth table. Now we have to choose one of the inputs as our selector for the next step. I'm using the A as my selector. Why? Because it's easier for me when I separate this table into 2 segments. And as you can see, I'm separating this table into 2 segments when the A is 0 and when the A is 1. Now, when the A is 0, I can conclude the cout is equal, the cout output is equal to when the B and sin using AND gate. And I can see when A is 1, the cout output is when the B and sin using OR gate. Now how can I do this? Is when we take a closer look here. Okay, this columns, you can break down it one by one. When the B 0 and sin 0, the output is 0, the B1, C is 1, etc., etc. And you can see the behavior, the characteristic of this output is, right? And I can conclude, and we can conclude that this behavior is exactly the same as the AND gate. Same as the other segment. I can conclude that this behavior, this characteristic of output is the same as OR gate. Okay, done. Next step is we want to make the multiplexer circuit. But before that, we have to know the basic about the multiplexer circuit. Okay, in this context, in this case, we have to take a look at the AND gate circuit, AND gate multiplexer circuit, and the OR gate multiplexer circuit, and how they work. Okay, now one by one, from the AND gate first. All right. Now we can see here there is 2 outputs, A, B, and Y. I'm using again A as my selector because it's easier. I separate the table into 2 parts when A is 0 and when A is 1. Now when A is 0, the output, the Y, is equals to 0. And when the output of the A is all 1, the output of the Y is equals to B. See, it has the same characteristic. the same number, the same output. So I can write those two in like this. Now, how about the circuits? The circuits approximately looks like this. As you can see, I'm using A as my selector, as I said before. B and 0 is my output, and Y as my B and 0 is my input, and Y is my output. Sorry. Now, move on to the OR gate. I'm using A as the selector, and when A is 0, the B, the Y output is equals to B. And when the A is 1, the Y output is 1, also 1. So I can write both like this. About the circuit, approximately it looks like this. I'm using A as my selector. This is B. Excuse me. This is B as my inputs. 1 also as my inputs. And Y as my output. Now here comes the little hard part. Okay, a little hard part. You have to listen to me carefully. Take a look at this big circuit. This is the circuit. It contains 3 multiplexer, 3 2 to 1 multiplexer. Okay, because the questions ask so. Now, I want you guys to have a look at these little parts of the multiplexers right here. I'm using 3. Okay, this multiplexer, this circuit is the AND gate multiplexer circuit. Okay, now we have to change the context. We have to change we have to implement based on our case. Now in this case, I'm using this truth table. Okay, why you guys asking why in this big circuit you are using B as your selector, but you said that you pick A as your selector before? Now hear me. Okay, this little circuit comes from this little segment, actually, guys. See, and as you can see, it has like similarities from this circuit and this theory, this material. In this material, I'm using A and B as my inputs and Y as my outputs. But in this case, I'm using B and C in as my inputs and C out as my output. Now, if we change all the context, this letter B equals to 0 is the same as C in equals to C out equals to C in. Because on this table, where is it? On this table, C out is equals to Y and C in equals to B and B is equals to A. Okay, only on this context. Okay, so that's why the B is the selector, the C and the 0 is my input. Okay, understand from that. The same principle also used on the other circuits. On this circuit, you guys can guess what circuit this is. This is a OR gate multiplexer circuit. Same principle also, I'm changing all the context here. I'm using B equals to A in this context, C in as my B, and C out is my Y in here. context. Okay, so same, I'm using B as my selector, CNN1 as my input, and the Cout as my output. Now, these two circuit, these two circuits has outputs, right? Now, both outputs from them, I'm using it as my inputs to the bigger or the last 2-to-1 multiplexer case. I'm using yellow is in here. Okay, the outputs from those previous two circuits begins to changing. Now it's my input. Now it's changing as input. Okay, now you know and you understand why I'm using A as my selector, the Cout from both previous circuits as my inputs, and the Cout as my output. It's because it's happening is from here, from this big explanation that I tell you before. Okay, you begin to understand. Now from that we can conclude that the implementation of Cout in the 3-2-to-1 multiplexer looks like this, guys. Now you understand. But if you guys don't understand, you guys have any questions, you can pick me up on the DM, you can hit me up on the WhatsApp or Telegram or anywhere you can find me on the campus. Ask me. I am free to have a discussion with you guys. Thank you so much. That's all explanation for me. Wassalamualaikum warahmatullahi wabarakatuh.